Okay, so this is our water sampling stand presentation. The primary and secondary roles for the rotational base, Kayla was the primary, Mason was the secondary. For the sampler stand, Mason was the primary and I was the secondary. For the pipette squeeze, I was the primary, Evan was the secondary. For the vision system, Evan was the primary, Dimitri was the secondary. And then for the control code, Dimitri was the primary and Kayla was the secondary. So to kind of summarize, the project goal was to successfully develop a device to take 1 milliliter of sewage water using a pipette and then transfer the sample to a container using a vision system and control code. This device consists of separate pieces and mechanisms that work together to test the water sample for COVID-19. And this project contains a sampler stand that uses a vision system and a pulley system to hold and lower the pipette. It also contains a rotational base, a control code that controls the pulley system, the pipette squeeze, and the rotational base. It includes a vision system and a pipette squeeze.
The constraints of the design, the variables we considered are materials that were provided in the kit. So we had to use the servo motors and all the stuff that was in the kit in our design. The deadlines, I think, were the biggest part. We had to maintain the budget, all our resources. We had to write down where we got all our materials, how much they cost. I think availability, everybody meeting up together is the biggest constraint of the project, but we made it work.
As far as team meetings go, we had as what could best be characterized as being a very Socratic method of performing team meetings. We would make sure to give each other ample time and our thoughts and our ideas. And obviously right here listed the majority of what was discussed on the primary dates that we did discuss them. Obviously, as the screen says, we assigned roles and we did what was needed in order to be able to complete our project in a timely manner. But what can't really be shown on paper or on a screen is that we did collaborate together very well.
For the rotational base, I had to do the calculations for how big the gears were. There was a gear attached to the stepper motor and one to the I guess like the platform the cups were sitting on. And so when I did those calculations, it turned out that it would turn about an inch a second, and that was well within how fast we needed it to go. I guess that pretty much sums up the calculations. For the cost analysis, I tried to include everything. I think I've got the kit, the servo and everything in there. With labor and everything, it ended up costing almost $236. And this is a model of the design. I tried to show where the servo was integrated into it, so I put the isometric drawings in. I think it's pretty accurate. And that's what it ended up looking like when it was all done.
For the sampler stand, I was the main guy for that, and the initial calculations for that was trying to find the center of mass. So we had a ballpark idea of how much weight we were going to have with the pipette squeeze and the motor moving up the pipette back and forth and such. And so we went back and forth, and we came out to be having the center of mass at about 6.784 inches, which we kind of overkilled a little bit to have more room than we needed. So it was a lot easier to take away material than it would be to add material. So we just want to make sure that the integrity was strong enough that it would hold everything up and that the sampler stand wouldn't move over. If it happened, it would break, then that would be catastrophic. Here's the cost analysis, and as a lot of our parts were from the kit, also just as much were parts that we already had, so we had to do an estimated guess. And the total cost came out to be about $225 for the sampler stand. and it was about 5 hours of work. And we really didn't need that many pieces. It was a pretty simple piece, but total for cost on materials, you can see the bottom right was about $28.27. But then with the hours of work and the pay for the work, it was $225. Here's a 3D stand, the 3D model of the stand. And as you can see in the far left corner on the top, there's the top gray arrow, the short one. That is for our pulley to move the pipette up and down. And then the long arrow pointing down on the other cylinder, that is for the motor that moves it up and down. And you can see the other side of that. And there's our measurements on the right side too. This is our final project. Looks a little bit different than the CAD model, but it's in very, very close. We 3D printed the spool for the motor on the back to move up and down, and we had to use a spool for the top to make it where it would slide to get rid of friction. We had a trouble with that on the beginning. Our initial design wasn't that, and it was just sliding on a board with keepers on it, but it kept getting caught, so we ended up putting like the spool on the top so it also was able to slide. It diminished friction and was able to move the pipette much easier.
So for the pipette squeeze, the main calculations were calculating the torque needed for the servo motor. The servo could generate 1,600 grams per centimeter of torque. And while building the design, I did run into a problem with getting the arm to squeeze precisely. So I had to go in, we made some changes there so that it would squeeze the correct amount of water from the sample. But overall, it ended up working really well. And I also had to consider not to block the vision system because the vision system was placed kind of in the sampler stand behind the pipette squeeze. So the total cost to build the pipette squeeze was $242, just based on labor cost and then the cost of the materials used. And this is the 3D model for the pipette squeeze. The gray arrow points to the servo motor where it's placed. And this is the arm that squeezes the pipette. And this is what the final design ended up looking like. And then this is for the vision system.
So for the vision system, we were able to perform this in such a way and set it up to where it was able to work with the pipette squeeze and also the sampler stand. The idea, of course, was talking around and listening to what other teams were planning. They were just overcomplicating it, in my personal opinion, with having multiple stands and setups that would take up a decent bit of room. Ours was very compact and tidy. And so with the talk and look at all the distance and whatnot, we were trying to find the best way to capitalize on our rotational base, our sampler stand, and overall keep our dimensional size very compact while also making it work with the software. And as far as cost goes, it was in total $13.98 because all it really took was taking off the clip that already came on the camera, gluing it to a piece of wood and being able to stick it as far back or as close forwards as we needed to in order for the camera to be able to most accurately read what it was looking at. And that's the little block of wood that we fabricated together in order to mount the camera to.
Can you read
So-
that, Dimitri?
Yeah, I mean,
Okay.
yeah. So the control code calculations are regarded practically the positioning of the pipette squeeze, how fast we wanted the rotational base to turn, and practically the pressure applied on the pipette in order to obtain 1 ml of the sample practically. Now, the control code cost analysis, as we see, was a total of $22 for the Arduino, only the board practically, and the labor cost was around $270.
This is
So,
the control code, but I'm not going to have you read through it, I guess.
no, I'm not gonna read through it. I'm just, yeah, I was gonna say generally that once you create the through the help of Guide, which is a program on MATLAB, once the GUI, the graphical user interface, was created, it had provided a general template, which forward on, I proceeded to write down the code with comments on each code regarding what each code operates on the sampler stand. You can continue after this. You could continue. Right, so here we start off with, as we can see where it says base clockwise toggle button, that's where the first code for the first toggle button, which regards the base rotation in a clockwise term practically. Now, this is where I integrated a counterclockwise spin for the stepper motor, again regarding the base rotation. Continuing, we have the pipette, the lowering and hiring of the pipette, which was again controlled by a stepper motor. In this specific occasion, it was for a clockwise rotation. That's the code starting over here. In continuation, if can you go one slide back? Sorry.
Yeah.
This is the code for the servo motor, which controls the pipette squeeze, which was used for, in GUI, there was a slide bar, which when controlled, it moved the servo to our desired need, either 180 degrees or, yeah, or so. And this is our final part of the code, which controls, again, the lowering of the pipette squeeze, of the pipette, excuse me, but in a counterclockwise spin, again, for the stepper motor. And this is a general flow chart, as we can see. This was the final GUI interface that was practically managed to be controlling the sampler stand and the whole process.
Yeah, so this is the overall 3D model of our design. As you can see, there's the sampler stand that contains the pipette squeeze. And there's not a pipette in this demonstration, but there is in the real design. And then there's a hole for the vision system. There's the rotational base and the divider between where the two containers are placed. And then at the top represents the pulley system. So for the Gantt chart, we had a schedule kind of laid out, and we didn't exactly end up following this schedule due to some time restrictions. And I think some of our demonstrations didn't end up getting done at the exact time we thought they would. But overall, we tried to stay on track with this schedule.
We'll add one thing to that as well. We, for one of the main reasons that we weren't able to finish on specific times was because we were running into troubles like we talked before about the friction of the pipette moving up and down and such, and like where to place the vision system and everything. It took a little bit more collaborative thinking on some of those things and some setbacks. We got it all built and it wouldn't even pull our, did change some things, but we were able to figure it all out. So
yeah, and we did also have some issues with the pipette squeeze as well. The arm was giving me a little bit of complications, but we all came together and tried to throw out ideas to fix the arm to where it would squeeze properly. And in the end, we figured it out.
And to continue, general overview of the economic analysis. We took into consideration the total cost of the materials used, as well as the labor cost, which in total came out to a final cost of $1,123.70.
So this is a picture of our final design, and the design did work successfully. We have posted a video on YouTube of our final demonstration of the design working together.
So in conclusion, the water sampling machine worked as intended. All functions acted as required in the project description. The fluid was extracted, placed upon its new desired location. The control code worked flawlessly, and each component functioned with ease. We had no trouble with the rotational base sponge, picked up exactly 1 milliliter of water and moved it up and down with ease after fixing our problems. And long and short, all components worked with the directions, boundaries, and expectations. Water sampling was a success, just as was intended.
So I think we're done.
Thank you.
All right, thank you.
Yes, thank you.